So today I'm going to talk to you about using the oscilloscope. Professor Goddard mentioned this yesterday, the big fancy ones we have in the lab that are $30,000, if you remember that. And this one is the $25 one, I believe, or somewhere around that price range. So what an oscilloscope is a measurement device that allows us to see a signal changing over time. So with the multimeter, you can just see one value at that instance in time when you're measuring across like a resistor, a voltage, a current. The oscilloscope is useful for seeing a voltage, but over a period of time. So you can see, like, if you have an alternating signal, you'll see the signal appear on the screen. So your y-axis is going to be voltage, and your x-axis is going to be time. So I'm going to turn this on here. If you want to just watch to start, I'll go over the basic controls. So right now, on the projector, you can see that there's just noise because the wires aren't attached to anything right now, or the probes. So if also on the oscilloscope, this one has a 1 kilohertz signal just automatically generated for you. And that's the little knob at the top. So there's a little metal piece, and that's going to give you a 1 kilohertz signal. So to measure that, okay, do you just ground it?
AC is fine, and then disconnect the power for the red. Don't worry about the black.
Oh, okay. So if we plug this in, you'll see a signal appears. And it's a 1 kilohertz signal, and we can tell that because at the bottom you can see what your measurement values are. So the oscilloscope screen has a grid on it, and on the left we see 1 volt. That means that your Y increments are in 1 volt. So we can see here that it goes about 1.5 squares high, which means your signal is alternating between 1.5 volts positive and 1.5 volts negative. And then to the right, you see the 0.5 milliseconds. That means your time, or your x dimensions, the distance, or your x coordinate dimensions are in 0.5 milliseconds. So
every box or every tick?
Every box.
Every box,
Yeah.
0.5 milliseconds.
Yes, every box here is 0.5 milliseconds. You can see one signal takes about 1 millisecond. If you do the calculation, so frequency is equal to 1 over the period of a signal. So 1 over 1,000 is 1,000th, which is 1 millisecond. So that's how that relationship works. Hertz milliseconds, yes. Or seconds, and then it's 1,000th of a second. All right, so if your signal, let's say it wouldn't fit on this screen, this one is a pretty nice signal for example purposes, but how you can adjust the oscilloscope is on the left. If you press V/div, this is your voltage increments. So if you press it so that it's highlighted, you can then use the knob to adjust what your increments are going to be. Okay. So up and down. You can see that the value is changing. Mm-hmm. So right now we're at 2 volts. You can see it's still the same signal, just on a different scale. Okay. When you're done adjusting your voltage, you could just press it again, so it's unhighlighted. And then if you go to the second division here, and you turn the knob, you'll see it spreads out or gets closer together. So your x increments are changing. Okay, so when you're happy with your signal, you can just press second division again, and it locks into place. So what a trigger does on an oscilloscope is it's a set value of y where the signal will start. So from the left, you can see the little tiny arrow right here. So that's going to be your trigger. So right now it's just set at the midpoint of the signal. If you click, oops, let me take this off. So right now it's on auto. That's sometimes the best one, just because if your signal's flying around all over the place, you might not know where to start. You can also change it to norm and sing. So I usually just keep it auto, that's the best place to start it. And you'll notice that the signal has stopped moving around. And this is because the oscilloscope has set it to hold. So it's going to hold your signal at place in that one time that it stopped. In order to start running the oscilloscope again, we get out of trigger and we press OK. And now you'll see in the top left corner that it says running. So if you want to stop it again, you just press OK, and it'll go to hold, and your signal will freeze at that point in time. Then we can have it running. The last feature for trigger is what's highlighted now, which is going to tell the oscilloscope whether you want to start the signal at the rising edge or the falling edge. So the rising edge is when your signal starts to increase, and the falling edge is when your signal will start to decrease. So if we change this, you'll notice that the signal switches around depending on whether you want the rising edge or the falling edge to be the start. Okay, I'm going to hold it. So now I'm going to exit out of trigger, so nothing's highlighted. I don't accidentally change anything. If you turn the knob, nothing will happen now because nothing's highlighted on the screen. All right. So are there any questions about the oscilloscope? Okay.
I'm going to ask questions.
Yeah.
So you mentioned that the oscilloscope allows you to view waveforms as a function of time. Does your signal need to be periodic to be able to look on the oscilloscope? Can you talk about like what types of signals you can measure, or typical voltage ranges, and so forth?
Yeah. So you can measure both AC and alternating current and direct current. If you measure direct current, you should just see a line because the voltage is staying the same across time. So the range for the oscilloscope, let's just see here. It looks like you can go down to 5 millivolts as your lowest, and up to 20 volts as your highest. So you've got a pretty good range, especially.
And that's per division, right? So with 8 divisions.
Oh, times 10.
4 divisions vertically, so you can measure up to 80 volts.
Mm-hmm.
Probably not safe, but.
Yeah, so for basic purposes in the projects you'll be doing in class, you won't be going over that. And if you have under whatever the minimum was, you're basically at 0 volts at that point, and you won't be able to power anything.
The trigger setting seen.
Sing?
Singular.
Yeah, I'm pretty sure that's just a singular value. Yeah.
Because I know some oscilloscopes you can put a microphone on and look at sound waves.
Mm-hmm. So yeah, so later you're going to be building an FM transmitter, I believe, or that's one of the projects in the kits that we offer. And there you can see like the radio frequency signal that you're sending, which is using a microphone. Yes, and then what was your other question? Oh, alternating versus direct. So yeah, if you just.
What are typical horizontal scales that you can see? Like what's the fastest signal, what's the slowest signal? It doesn't need to be periodic.
Yeah, so the fastest, we go down, it goes up to 500 seconds. And the slowest is going to be 10 micros, or the fastest is going to be 10 microseconds there. Okay. Yeah, wait, mine froze too. There we go. Is it in the like normal range? Because once you get too far on either extreme, it kind of freezes. Yeah.
You go on 5 seconds, 2 seconds, 1 second, 1.5 seconds, and it's not changing. Still on trigger.
Mm-hmm. Is it on trigger auto? And is it running?
Yeah, I'm on the same.
Okay, that might be the problem. So some typical voltages you see, right now this is just a square wave, and that's easy to remember because it looks like a square or at least a rectangle. You can also measure just sinusoidal waves, so just a slow up and down, back and forth over time. You can measure the direct voltage, which would just be a line across the screen, like 9 volts constantly. There's a triangle wave. I don't remember the right name for it, sawtooth. And that looks like diagonal lines, like rising up, then suddenly dropping, rising up again, then suddenly dropping. So you can measure that as well. So we're going to start by turning on the oscilloscope. You can turn it on at the bottom. It's plugged into power, just the bottom there. At the top, you can see I have an alligator clip on the 1 kilohertz signal. It's the little metal knob sticking out of the top of the oscilloscope. And the switch should be turned on to AC because we'll be measuring an alternating current signal. You also want your alligator clips attached and ready to probe your circuit and measure the capacitor value. So we start by having the 1 kilohertz signal just in one of the columns of your breadboard. You can choose any column, whatever is convenient. And this is the circuit we're going to be building. So we have the 1 kilohertz signal at the top. Then we need to connect that to a resistor. We're going to use the 10 kilo ohm resistor, which is brown, black, yellow. So put one leg in to the same column as the 1 kilohertz signal, and the other leg can just go into any other column on the side. Next, we are going to add the capacitor. The capacitor here is unpolarized. These smaller ones, the legs are the same size, so it doesn't matter which direction you plug the capacitor in. So we'll spread out the legs a little bit. Put one leg in the same column as the resistor, and the other leg can just go into another column. Finally, to complete the circuit, we need to put the black probe against the capacitor. And then the red alligator clip is going to probe in between the resistor and the capacitor. So you can do that just by adding it to the leg there. And this allows us to measure the voltage across the capacitor, which we'll notice there's a change in it. So you can see my signal on the oscilloscope has changed. Now it has a rising edge and a falling edge. So if you want to see the original signal going in, move your probe over to the left. You can see the original 1 kilohertz square wave. And then as we move the alligator clip over, across the capacitor, you can see the signal has changed. So why this happens is because in RC circuits, the capacitor needs time to charge and discharge. You can learn more about that in the Circuits 1 lecture. And how you calculate the time constant is the resistance times the capacitance. So our time constant here is going to be 0.1 milliseconds. And this means it'll take 0.1 milliseconds in order for the signal to reach around 67% of its value. So if we go back to the oscilloscope, you'll notice that from the lowest value to around 60% of the peak value is around half of a block away. Our time scale is 0.2 milliseconds, so half of that is 0.1 milliseconds, and we can confirm that the time constant matches what our theoretical time constant was. All right, so this is a good example for using the oscilloscope in your classroom.